The paper introduces a novel approach to enhance the explainability of face recognition systems by leveraging a face reconstruction module and a saliency map generation algorithm. It aims to explore the connection between facial images and deep features, providing a more transparent and reliable face recognition process. The face reconstruction module allows for the reproduction of a face image from its deep representation, which can be modified through forward propagation. This method not only highlights similar regions between two given face images but also dissimilar regions, offering richer explanations for the decision-making process of the face recognition model. The paper's contributions include the development of an explainable face recognition framework and a saliency map generation algorithm that provides insights into both similarity and dissimilarity regions. Extensive experimental results demonstrate the effectiveness of the proposed method in enhancing the model's explainability. The research paper emphasizes the significance of explainable face recognition, XFR, in deep learning-based computer vision systems. It highlights the uniqueness of face recognition compared to general deep learning tasks due to its comparative nature between two or more facial images. The proposed method focuses on identifying the most discriminative and dissimilar regions of two given faces that influence the deep model's predictions. The approach explores the direct affinity between specific discriminative feature channels and the input facial image through a forward propagation manner, leveraging a face reconstruction module. This method generates saliency map explanations by propagating critical deep features to a reconstructed face image, offering a novel solution to the limitations of existing gradient-based and perturbation-based methods. A novel explainable face recognition framework is proposed, comprising two streams, the recognition flow and the explanation flow. The recognition flow performs standard face recognition tasks, whereas the explanation flow utilizes a face reconstruction network to reproduce facial images from deep convolutional representations. The core concept is that any modification to the deep feature will be reflected in the rebuilt images, indicating the specific face region corresponding to the masked channel. The explanation flow also generates a novel explainable saliency map through an iterative process. This process involves feature extraction, iterative modification, and reconstruction, followed by the calculation of similarity scores. The similarity score, computed as shown in equation 1, represents a channel-wise importance weight for the residual maps. This score enables the decomposition of the produced discriminative saliency map into similarity and dissimilarity heat maps, facilitating higher-level interpretation. The explanation flow provides a mechanistic understanding of the face recognition process, allowing for the identification of specific face regions contributing to the recognition outcome. This framework offers a significant advancement in explainable face recognition, enabling the development of more transparent and trustworthy face recognition systems. The proposed explainable face recognition framework integrates a reconstruction-based explanation module, demonstrating similar or slightly better accuracy compared to the original ArXiv pipeline on 5 datasets. This framework uses a two-stream workflow, comprising a recognition flow and an explanation flow. The explanation flow employs a face reconstruction network with 4 transposed convolutional layers. Visual results show meaningful explanation maps focusing on critical facial characteristics like lips, nose, eyes, and mouth, varying for different subjects. In contrast, many other approaches failed to provide stable outcomes and meaningful explanations in certain samples. A quantitative evaluation using the hiding game methodology demonstrates the effectiveness of the proposed method in generating accurate saliency maps, outperforming state-of-the-art model-agnostic XFR methods. The overall loss function combines both the ARC face recognition loss and an MSE loss between the original and reconstructed faces, with a weight of lambda equals 1 for the reconstruction loss. The model is trained on the MS1MV2 dataset for 25 epochs, using the SGD optimizer for the face recognition pipeline and the ATOM optimizer for the reconstruction network. This method's ability to provide precise and informative saliency maps while maintaining recognition performance makes it a promising approach in explainable face recognition. In the context of deep face recognition systems, this page delves into the efficacy of a novel explanation method that decomposes saliency maps into similarity and dissimilarity components. Figure 2 visually compares the saliency maps generated by 6 distinct explainability methods, while Figure 3 provides a deeper analysis of the proposed explanation method's interpretation of a deep face recognition system's decision. The results show that the similarity map primarily highlights facial regions, whereas the dissimilarity map focuses on occluded parts. This decomposition allows for a more nuanced interpretation of the model's decision-making process, revealing that the deep model verifies the occluded image based on unmasked areas such as the eyes and forehead in instances of matching subjects. In cases of non-matching subjects, the dissimilarity map concentrates on critical facial areas, while the similarity map focuses on the backgrounds. Quantitative performance evaluation, presented in Figure 4, demonstrates the superiority of the proposed method over existing explainability methods, including GradCam++, Gradient, Styleanu et al., and XFace. The hiding game evaluation, which involves blurring out different percentages of the least important pixels, reveals that the saliency maps generated by the proposed method remain the most accurate. The area under the curve, AUC, metric, reported in Table 2, further validates the conclusion that the proposed saliency maps are more accurate in describing the most discriminative facial regions, not only on the LFW dataset but also on the HDB30 and CFPFP datasets. This page's content builds upon the previously introduced explanation method, providing a more comprehensive understanding of its capabilities and performance. The results underscore the significance of decomposing saliency maps into similarity and dissimilarity components, enabling a more nuanced interpretation of deep face recognition systems. The table below presents a quantitative performance evaluation of various face recognition methods on LFW, HDB30, and CFPFP datasets. It reports the hiding game AUC scores for each method, including GradCam++, Gradient, Styleanu et al., XFace, and the proposed two-stream explainable face recognition framework. Notably, the proposed method outperforms all others, achieving the highest AUC scores across all datasets. This superior performance underscores the effectiveness of the proposed framework in enhancing the explainability of face recognition systems.